In this video, we're going to introduce two ideas, one of which is the order of a group and the other of which is the order of an element of a group. And they're two somewhat different ideas, but as we'll see in this video, they are related in kind of a nice way. All right, so let's start with the order of a group. So suppose G is a group. Okay, so it's a set with an operation. Set with operation, just as a reminder. And usually when we talk about G, we're just referring to the set. The operation sort of comes along, but if I just write down G in casual conversation, usually I'm referring to that set and the elements of the group. Okay, so here's what the order of the group is. We define the order of G, which I usually write absolute value symbol G. So this doesn't mean magnitude in this case, this means the order of G. We define this to be the number of elements in the set G. And if G is an infinite set, which it absolutely can be, then we say G has infinite order, and we usually write that as just absolute value symbols G equals infinity. So order of G is infinite. Okay, so that's what the order of a group is. Now the order of an element of a group is a little bit more complicated. So here's the definition of that. Suppose G is a group. And let's fix an element of that group. So let A be an element of the group. The order of A, which is usually written this way. So again, I use the absolute value symbols. And this is a little bit tricky because sometimes we'll be in settings where the group elements are numbers, and we don't mean the absolute value of that number. We mean the order of that number as a group element. And we'll pretty much always mean that in this course, unless I say otherwise. So the order of A is the least positive integer n such that a to the n is the identity, assuming such a number exists. It doesn't have to. If such an n does not exist, if no such positive integer exists, then we say the order of A is infinite. Okay, so just to illustrate why it is possible that no such n exists, and this is also a good illustration of the idea of an infinite group, because I don't think we've had an example of that before. So here's an example. And this is a group that you're probably pretty familiar with. We've been talking about Z mod n and dihedral groups, but one thing we haven't talked about is the idea that just a very ordinary looking set like this, with a very ordinary looking operation, can be a group. So the integers under addition, I claim this is a group. So this is a group. Why? Well, we know Z is closed under addition, so this addition operation is a binary operation on Z. In other words, I can add any two integers and get an integer, no problem. So I know that. I know that addition is associative. We've known that since grade school. I know that 0 is the identity element, because any integer plus 0 is itself, and every integer has an additive inverse. And even better, this group is abelian. Because I know that addition is commutative. That's not required to be a group, but it's nice to have around. Okay, but how many elements does this set have? Well, as we've known for a pretty long time, this is an infinite set. So I can say that the order of this group is infinite. And for now, we're not going to worry too much about whether it's countably infinite or uncountably infinite, although that can be interesting to think about sometimes. For now, we'll just take note of the fact that this is an infinite group. Okay, but what about orders of elements in this group? And remember, I'm using this to mean the order of 3, not what is the absolute value of 3 in this group. Well, to answer this question, I need to figure out whether there is some positive integer number of times that I can operate this element with itself so that I will return to the identity. That's the idea here, is I have to figure out how many times I have to compose 3 with itself using the group operation in order to obtain the identity. Well, let's see if I can do that. Now, the thing to keep in mind here is that the group operation here is addition, so I'm not going to be taking powers of 3 in the literal sense, like I'm not taking 3 to the first, 3 to the second, 3 to the third, 3, 9, 27. I'm taking what we're sort of calling powers of 3 under the group operation. So if I start adding copies of 3 together, because addition is the group operation, well, there is no number of those that is going to get me to 0. This just can't happen. So there is no power, and I'm using power in quotation marks, there is no number of 3s that's going to give me the identity. So the order of 3 as a group element here is infinite. Okay, so it's possible for the order of a group to be infinite, it's possible for the order of a group element to be infinite. Here's maybe a better example, a better illustration of the concept, because it's kind of weird to start with an example where the order is infinite. So let me give one where the order is finite. Let's take Zmod 6. That's kind of a nice example. So Zmod 6 has sort of a similar concept to Zmod 5, except this time I'm working on a clock face with 6 stopping points. So 0, 1, 2, 3, 4, 5. Okay, so that's a group. Its order is, well, 6 because there are 6 group elements. So now the question that we might ask is, okay, what's the order of 3? Again, the operation is addition, so our group is Zmod 6 under addition, which means that when we're thinking about the order of 3, rather than taking multiplicative powers of 3, we're sort of taking additive powers of 3, which means we're adding 3 to itself. So what is that? Well, I know that 3 is not equal to 0, so the order of 3 can't be 1. But if I add 3 to itself, so this is sort of like taking the second power. If I add 3 to itself, then I get, let's just march along the clock here, start at 3, 1, 2, 3. I get back to 0, which is my group identity. Okay, so this means that n equals 2 is the smallest power of 3 equal to the identity, which means that the order of 3 is 2. Now, the reason we have to be attentive to the smallest is someone else might come in and say, well, I noticed that 3 plus 3 plus 3 plus 3 plus 3 plus 3 is 0, because I know that if I take any group element at all and add it to itself 6 times, I'm going to end up back at 0. You can actually check that that's true. And you might say, well, that means the order of 3 is 6, but that's not true because we're looking for the smallest power of whatever group element we're working with that gets us back to the identity. In this case, that is 2. Okay, so that is the definition of the order of a group element. In the next video, we'll talk about a nice little theorem involving orders of groups and orders of elements.